Hello again. So we have reached the chapter Bipartite Graphs and Matching. So we'll be characterizing a bipartite graph. So we already know what's a bipartite graph, and then we will talk about matching, which is a very important problem in graph theory and mainly job assignments. And we will be implementing and focusing about the augmenting path algorithm and the Edmonds Blossom algorithm. So let's start with the characterization of bipartite graph. So we know that a graph is called bipartite if the set of vertices can be partitioned into two non-empty subsets, let's say V1 and V2, such that if there's an edge, X and Y edge is an edge of the graph, then X and Y belongs to a different subset. So we already know that we should have V1 and V2, and there's no edges in the set V1 and there's no edges in between the vertices in V2, but there can be edges in between both sets. So V1 and V2, they are called parts or bipartition sets of the graph. So it's common practice to assign one color, for example, red or blue, to the vertices of V1 and another color to the vertices of V2. Thus, a bipartite graph has the property that each of its vertices may be colored either red or blue, of course, so that adjacent vertices are of opposite color. So we have here P6, so this is an immediate example. So the vertices can be colored red and blue, so one red, one blue, and we can alternate that. So we can see that it could be colored like this, and so it could be done like that. So the partitions, each partition contains three vertices. The red would be considered as V1 and the blue as V2. So I can redraw this like this. So this is red ones, and those are the blue ones. So again, also for KMN, it's indeed bipartite. So the vertices of the two parts can be colored also either blue or red respectively, and each edge of this KMN is incidence with one blue vertex and one white vertex. So it should be clear from here that all trees obviously are bipartite. So we classify bipartite graphs as follows. So if I have a graph which is bipartite and its vertices are partitioned into two subsets V1 and V2, so usually the number of elements in V1 or the number of vertices in V1 is greater or equal than V2. So if I have the number of V1 is equal to the number of vertices in V2, so we call the graph equitable. If the difference is at most 1, so if the absolute value, the difference of the absolute value is equal to 1, it is called the graph nearly equitable. And if the distance or the number is greater or equal to 2, so it's called skewed. So let's see some examples. So you need to decide whether the first graph or the second is equitable or nearly equitable. So we have it's obvious here that if we color, for example, red, blue, red, blue, red, blue, so we have the number of red vertices is equal to 3 and the number of blue vertices is equal to 3. So we have here P6. So P6 is equitable, however P5 is nearly equitable. So we can say that Pn is equitable when n is even and it's nearly equitable when n is odd. So another exercise is for cycles. So the analysis of cycles is more interesting. So we see that, let's take this one, C6. So when n is even, so Cn is bipartite. So red, blue, red, blue, red, blue. So it's bipartite and is equitable. However, on the other hand, when n is odd, we can see that it's red, blue, red, blue, red. So red and red. So obviously, odd cycles, they are not bipartite. So we cannot say, so it's wrong to say if it's equitable or not equitable, because at the beginning, the cycles are not bipartite. So odd cycles are not bipartite. However, even cycles are equitable and bipartite. So how can we check if a graph is bipartite? So we'll be doing like this. However, in theory, we'll be using A and B instead of red and blue. So we label any vertex V by A, red or blue. So we're just using alphabetic A and B, and then we label all adjacent vertices of V by B. So all the adjacent are B. So, and if there are unlabeled vertices adjacent to a labeled vertex V, then label all vertices adjacent to V by using the opposite label. So this is the step 3. So we'll continue like this until, for example, if I have just one connected component, I will either find something wrong, or I could color them with A and B. And if I have finished the one connected component, I can move to other connected component, and obviously I will repeat the steps 1 to 3 and so on. So there's no need to write all these. So we'll check it on the example. So we have two graphs and we need to check if they are bipartite or not. So let's start from here. We can pick any vertex. So let's say I'm starting from C, so I will label it with A. So all its adjacent vertices, I will label them with a B or blue. So B, B, B. Then I need to continue from, for example, from E, F, or B. So E, I need to color its adjacent vertices by also, so A by the opposite color. So I should color D by A, G by A, J by A, and B by A. So obviously I have here a wrong matching, so it's not bipartite. So I cannot consider this graph as a bipartite. Another example. So again here, let's start, for example, from a K. So I will label it by A. So its adjacent vertices O and N would be labeled as B. Then, for example, I pick O, O, P, it would be colored as A, and M and H, and I just have now L. So I have its neighboring or its adjacent vertices are K, M, and P, all of label A, so I can label it B, and this is a bipartite graph. So I can redraw this graph in a way that I have the vertices labeled A on a set and those labeled with B on another set. So we can see that the graph H is bipartite. So we have a theorem here that a graph is bipartite if and only if it does not contain, if G does not contain any odd cycle, an odd cycle. So it's very obvious, because if there's an odd cycle, so for example like C5 or C3, it means that I have one vertex, one set of the vertices, there's a link between the set, and it will be not bipartite. So obviously all trees, they are bipartite. So we have an exercise here. We need to draw all connected bipartite graphs of order 5. So we have to draw with 5 vertices. So we are organizing our graphs according to the number of edges. So first we have all these with 4 edges, so they are all bipartite. So I'm picking K1N, K14 here. We have here K1 plus K1 plus K1 plus K2 bar. So it's very obvious to see that. We have also here a P5. As for this graph is equal to K1 plus K1 plus K2 bar plus K1, and this one is K2 3. So you need to practice this in order to find all connected bipartite graph. So this is for the characterization. We will move to the more important part, which is about the matching and job assignments problem. So what we call a matching. So a matching, usually it's represented by the letter M. So a matching in a graph is a set of edges, no two of which are incident with one another. So in other way, I need to match vertices between these two sets. So bipartite graphs are important, particularly in applications involving matching problems. So why? Because if I have a bipartite graph, so I can match a vertex from V1 to a vertex from V2. So suppose that certain workers can operate certain machines, for example, but only one at a time. This gives a bipartite graph between workers and machine. And if you want to have many machines operating at the same time, we need a larger matching in our bipartite graph. So usually it has a lot of applications. So example, a company may have a number of employees qualified to perform various jobs if there are several tasks to be done. So how should the company assign the employees to the task to maximize efficiency, for example? So the job assignment problem is of uttermost importance when there's a strike, and management personnel must try to cover the job of the striking employees, like in our case at the university. So again, also when students apply, for example, like you to university, so each student has a list of university preferences, and each university also has a list of preferences for students. So in order to decide which students should go to which university, so we need to find a bipartite matching that is somehow compatible with these preferences. So this kind of situation is called the stable matching problem, and it's extremely important in economics and operation research. So this is what we will cover in this part. So it has an outline. So in this section we'll discuss matching in bipartite graph with particular attention to the job assignment problem. We then discuss matching in more general graphs and how to find matchings of maximum size in a bipartite graph. So you need to pay a lot of attention about this part. So we consider that we have a graph which is bipartite with two parts, x and y. So this is always the case. So a matching M, we recall it. So a matching M, such as every vertex in X is incident with an edge of M. So it's called complete matching from X to Y. So if every vertex from X, I can match it with a vertex from Y. So this is just from X to Y. So if I want a complete matching from Y to X, it means I should match every vertex from set Y to a vertex in the set X. So in the case I have both matching, I will call the matching a perfect matching. So if I can find a complete matching from X to Y and from Y to X, I will call it a perfect matching. So in this particular case, obviously, the number of vertices in X should be equal to the number of vertices in Y. So in other way, the graph is equitable. So a complete matching from X to Y requires merely, so here I have the inequality. So it's X, the number of vertices in X is less than or equal to the number of vertices in Y. So it's important in applications to determine whether a bipartite graph with parts X and Y has a complete matching from X to Y. So this is very important because we need to match all vertices in each set. So let's take, for example, an example. So let's suppose here we have applicants for job. So those are the applicants A, B, C, and D, and those are the job in small letter A, B, C, D, and E. So obviously there should be a matching between the person qualifications and the job requirement. So the situation can be described by a bipartite graph, and it is as follows. So let the vertices of X represent the applicants, and let the vertices of Y represent the job opening. So we draw a vertex, or we draw an edge from a vertex V in X to a vertex W in Y whenever the applicant represented by V has the skill required, obviously, by the job represented by W. So the degree of V, so here, for example, 2, the degree of A, so indicates how many jobs whenever the applicant represented by V is qualified to do. So A is qualified to do 2 jobs, D is qualified to do 3 jobs. And the other way, the degree of vertex W shows the number of qualified applicants to this job. So we can find a matching. So let's try to find a matching here. So for example, I can match A to A, B to B, C to C, and D to D. So this is one matching. So I can find another matching also. So for example, I can match C to C. So this is obvious. I can match B to D, D to E, and A to either B or A. So as you can see, since the number of applicants is 4 and the number of job opening is 5, so obviously one of the job would remain open. So as you can see, also there is many possible matching. So how can we find? So how we are able to describe precisely when a bipartite graph has a complete matching? So we need to know when it has a complete matching. So we'll define what does it mean a complete matching. But in order to establish this result, we need to technique for obtaining a matching of largest possible size. So I need to find a way to find the largest possible matching. So for example here, if I matched C to other jobs, so for example if I match C to D, so no one will be able to pick C. So this is very important to note that. So how do we find a maximal matching? So the in this example, so the darkened edges, so they constitute a matching. So we say that B is matched to D, E is matched to F, and A is matched to H. So obviously all these graphs are bipartite. So we say that a matching M is maximum matching, so if M has the largest cardinality among all possible matching. So as you can see here, I have a maximum matching, so I can match all the vertices. However, a maximal matching is a matching such that there is no larger matching containing M. So this is a maximal matching. Why it's a maximal matching? Because I cannot match C and G because there is no edge between them. However, if I have matched the vertices differently, I could have matched all the vertices. So what we are looking for is a maximum matching, but in sometimes I'm obliged to have a maximum matching because I don't have an edge. Just to pay attention to that, we will be looking for that. So if I can find a maximum matching, I should find a maximum matching. So we'll see ways also and algorithms to find maximum matching, obviously. So whenever I have a matching M, let's define what we define by alternating paths. So an M alternating path, so it's a path whose edges are alternately in M and not in M. So I prefer to show it here on the example. So for example, an alternating path, so it should be whose edges are alternately in M and not in M. So for example, C, E, F, G is an alternating path because one edge is not matched, the other is matched, and then is unmatched. So as you can see, we have also the notion of M match. So a vertex is called match. So sometimes we call it saturated. So if it so by the matching M, obviously, if V is incident with one of the edges of M. So for example, E is matched, F is matched, G is not matched because it's not matched in our matching M. So if it's matched, we call it matched or saturated. If it's not matched, we call it unmatched or unsaturated. An M augmenting path, so it's an alternating path. So it's alternating between matched and unmatched, plus the starting vertex and the end vertex, they are not matched. So for example, C, E, F, G, it's an M augmenting path. Augmenting because we are starting from an unmatched and we are reaching an unmatched. For example, B, D, F, it's an alternating path because I have one matched and one unmatched. So, and you should know that the most useful technique for finding a maximum matching, we will see later in this course, or this today in this lecture, so is based on the concept of augmenting a path. So again, so I have here C, E, F, G, so it's an M augmenting path. So because CE is not in the matching, EF is in the matching, and FG is not in the matching. Also, I have C, E, F, A, H, G is also an M augmenting path. So as you can see, a graph may have several M augmenting paths. So, and notice that an M augmenting path always begins and ends with an edge that is not in the matching. So, the following theorem of Birch, so you need to learn the name, characterizes precisely when a matching is maximum. So we say that a matching M in a graph obviously is maximum if and only if there is no augmenting, there is no M augmenting path in the graph. So whenever I have no more augmenting passes in the graph, it means that I have found the maximum matching. So obviously this is a good example because this is the same example here. Since I have found augmenting path, it means that the matching is not maximum. It means that I have to do something more in order to find the matching. And also I will give you a hint. As you can see, whenever there's an augmenting path, look well, I have changed the type of the matching. So as if I have flipped the type. So now CE is matched, EF is not matched, and then FG, so it should be matched. So we will see that how it will work. So whenever I can find an augmenting path, I need to flip stuff. So as you can see in this example, there's 2 augmenting passes, and we will see it later how we will work on this. So I will not take too much time. So here's the algorithm. So before reading the algorithm, because it's very picky, I will show it directly on an example, and then we will go back and check the steps. So I have here a bipartite graph, obviously. So I have here vertices 1, 2, 0, and 3. So if I want to color these vertices, for example, red, blue, so you can see, so it's bipartite. So I will find first one matching. So arbitrarily, I will match 2 vertices from each set. So let's say I have matched 0 and 2. And then, so I need to find an augmenting path. So in order to find an augmenting path, I need to find, to start from a non-saturated or a non-matched vertex. So I can either start from 1 or 3, because 0 and 2, they are already matched. So I need to start either from 1 and 3. So I need to find an augmenting path that starts either from 1 or from 3. So since it's undirected graph, it will be the same. So an example here of an augmenting path is 1, 2, 0, 3. So if I find an augmenting path, what I will do is that I will flip the matching. So now I will match 1 and 2. I will remove the matching from 0, 2, and then match 0 and 3. So I will continue like this until there is no more matching. So obviously in larger graphs, I could have multiple options. Also, I can start, for example, from 1, and I could not find alternating path or augmenting path. So I need to pick another one. So let's go back and see the steps. So first I need to find any matching. So let you denote the set of unsaturated. Unsaturated here, it means unmatched. So for example, in our example 1 and 3, so I need to start from any of these vertices. So if U is empty, so if there's it means that all vertices are matched, it means I have found the maximum matching. Otherwise, I will select any vertex which is unmatched. So I will consider Y in the neighboring of X. So if I'm considering 1, it means 2 is its neighbor. So if Y is also unsaturated, so obviously if I have two unsaturated, it means that I need to find, so if Y is also unsaturated, then add edge XY to M to obtain a larger matching M prime. So it means that if 1 and 2, they are not saturated, not matched, so I can match them. So this is very easy to see. And then I need to return to step 2 in order to continue the algorithm. Otherwise, if Y is saturated, like in that case, I need to find an alternating path. So if I can find an alternating path, I switch the edges, and obviously in order and switch and modify the matching. And then, of course, I will repeat the steps until the algorithm finishes. So if the path is not augmenting, so obviously I need to choose another vertex and repeat. So this is the idea of the algorithm. So I need to pick any matching, try to find augmenting passes, and then do the flipping and continue like this until the algorithm finishes. So obviously implementing this algorithm is a bit tedious. So this is why we will be considering Kuhn's algorithm. So Kuhn's algorithm is a direct application of 𝐵 lemma. So this is a 𝐵 lemma, and it is a bit modified. So first we take any empty matching. Then while the algorithm is able to find an augmenting path, we update the matching by alternating it along this path and repeat the process of finding the augmenting path. So as soon as it's not possible to find such paths, we stop the process, and the current matching is the maximum matching. So it's very easy. I just need to find augmenting passes and continue like this by flipping till there's no more augmenting passes. So in our example, so we have here the graph. So we have here the output. So we can find 4 matching. 3 would be matched to 0, 2 to 1, and 1 to 2, and 0 to 3. So obviously, because our graph is not directed, if our graph is directed, obviously I find here 2 matching. 1 will be matched to 2, and 0 will be matched to 3. So before moving to the exercise, let's do the implementation on a Moodle. So let's see. So they are asking us to implement Kuhn's algorithm seen in the lecture. So the prototype is just a function that solves, and we return an integer. So we will see what solve should return. So the following are defined globally. I have the FS white and black. So obviously this is for the bipartite in order to check if it's bipartite or not. So we will see if we will use them or not. We have the pair of integers. We have the vector of integers. We have the adjacency list. It's a vector of integers. We have a vector of matching. So we need to say which vertex matches to which vertex. We have the DFS number, obviously, because we were doing DFS in order to loop over the vertices, and we have V. So we know that we have a function read that reads the input. So let's see the test. We have read, we have a print found, %d matching, solve. So solve should return the number of matching in the graph, and then I will loop over the vertices and I will display the matching. So if match of I different than -1, so obviously I need to initialize match to -1, and if it's not -1, I will display its matching. So match I and I, so I have the matching. So for each vertex I have the matching at the beginning, and I need to write the solve. So let's start. I have int solve, and let's see what we will do. So obviously I need a counter because I need to return it. So let's call it, for example, maximum matching. So let's call it max match, and I should initialize it to 0, and I will return it at the end to display it by the function. So obviously, as I have said here, match should be initialized to -1, so assign. So I have V value and all initialized to -1. So this is for the matching. So V is the number of vertices in the bipartite graph. So then I need to loop over. So before solving this, so obviously since I need to continuously finding augmenting passes and finding matching, so I will write a function that find augmenting passes. So at each time I will count the number of matching and I will add them to the maximum match. So I need to loop. I will loop over the set of vertices. So for example, int L equal to 0, L less than V, L plus plus. So we will do some resetting. So I need here another vertex which is called the visited, or because I need to know which one is visited. So I can, for example, use the DFS num. So DFS num dot assign. So why I'm doing this? Because I need to flip the matching. So as if I'm changing the matching. So I need to assign V, let's say DFS white, as if I'm having the graph as not visited. And then I will add to the maximum matching the result of my augmenting passes. So plus equal, let's call it augmenting, and I will try to start from L. So this is it. So this is for the matching and the number of matching. So at each time augmenting, it returns the number of matching, so the new number of matching, and at each time I will reset the DFS to white. So I need to write the function int augmenting pass, and I need to start from a vertex. So let's call it L. So it returns 1 if an augmenting pass is found. So this is the just if an augmenting pass is found. So return 1 if an augmenting pass is found. So let's see. So if I've already so DFS num of L different than 0, so it's already visited, it's already counted, so there's no need to continue. So if DFS num of L is different than 0, so it means it's not white, so I return a 0. So let's call it, so if DFS num is different than white or is equal to black, it means it's already visited and it's already matched, there's no need to continue. Otherwise, it means it's white. I should make it black, so it's already visited. and then I need to loop over its adjacency, its neighborhood. So for in j equal to 0, j less than casting, so integer adjacency list, so I will copy the adjacency list here, I, so L here, dot size, j plus plus, then so I will take, so we have here a vector of integers, so let's say int r equal adjacency list of L of j. So this is the one. So how can I find a matching? So since I have the match list, the vector, so I will say if it's already if matched, so if R is not matched, so since I'm finding an augmenting path and I should start from a non-matched vertex, so if R is not matched, or recursively I can find an augmenting path that starts from R, so augmenting match, so it means here, so if match equal to -1, I will do a matching and then I will return 1. So if it's not equal to -1, so it means it's matched. So if I can find an augmenting path from R, so what I should do that is that I would say that match R is equal to 1, so it's matched now, and obviously I need to return 1. It means I have found a matching. So if I have looped over all its adjacent vertices and couldn't find any matching, I will return 0. So it's not I didn't find any matching, it means I couldn't find an augmenting path. So obviously here there's no matching. In that case, it means I have found one matching. And this is it. So let's check. And so the output is correct. So let me repeat quickly. So in the solve function, we have the number of matching. So we have assigned first the value of -1 to all values, and then we have looped over the set of vertices and we try to match it, to match each vertex. So this is why we have the assignment of the FS white for the FS number at each iteration. So we are resetting another way the DFS, and at each time I have a function called augmenting. So it's a recursive function that will return 1 if I could have matched this L with any vertex. So in our matching augmenting function, so if it's black, it means already matched or it's already visited, so there's no need to revisit it. Otherwise, I will loop over its vertices to find an unmatched vertex. So I have picked one. So if R is unmatched, so the adjacent vertex is unmatched, so it means I have found a matching. Otherwise, if I can find an augmenting path from R, I could match it, and I will say that L is matched to R, and then I will return 1 in order to find the number of matching. So this is it, the algorithm. It's very useful and it's very neat and simple. So let's do an exercise. So we have here some of the Faculty of Sciences staff members contracted coronavirus, so it's common these days. So thus these members were obliged to stay home. So management have decided that 4 jobs, enrollment, examination, security, and vice director, are essential if business is to continue during the absence of the infected members. So 2 people are needed for enrollment. So we need to find a maximum matching to determine whether all key jobs can be covered by the various employee. So 1 employee per key position if their capabilities are as described in the table on the next slide. So we have here the employees and what they can do, and we have 4 jobs: enrollment, examination, security, and a vice director. So I will represent obviously the employee by set V1 and the jobs by set V2, and obviously we will do some so there's an edge between, for example, an employee and the jobs that he can do. So we have here the employees, and here we have the job. So we draw the bipartite graph for each vertex in part X correspond to an employee, and each vertex in part Y correspond to a job. So since there are two people needed for enrollment, like here, so we have two separate vertices for those two positions labeled E1 and E2. So and an edge is present between person A and a job B if the person A is qualified, obviously, for the job B. So the resulting graph is shown here, and also we can, for example, show here a maximum matching. So as you can see, all the key jobs are covered. So this is what we call a maximum matching or a perfect matching. So it's a matching for which every vertex is a match. So it's maximum matching, obviously. So a perfect matching is a matching for which every vertex is a match. So it's the same as maximum matching. So in a bipartite graph with partite set X and Y, a perfect matching can only exist if there are the same number of vertices in part X and Y, obviously. So it means that the graph should be equitable. So we already said that. However, this condition is not sufficient. So it doesn't mean if the number of vertices is equal, it means that I can find a perfect matching. So here's, for example, an example. I have here a set V1 and here I have a set V2. However, I cannot find a perfect matching. So if I can match those two, obviously I cannot match the third couple. So, and this is the case. So if you do take all the possibilities, you cannot find a perfect matching. So we'll move to the third part, which is about the complete matching in bipartite graph. So we will consider the problem of when a bipartite graph has a complete matching or when it has a perfect matching. So this is why we will consider Hull's matching theorem. So the following theorem characterizes precisely when a bipartite graph has a complete matching. So for any vertex V, we know that the neighborhood of V is the set of all vertices adjacent to V. We already covered that. So for any set of vertices, so if I'm considering a set of V, so the neighborhood of the set of vertices is equal to the union of the set of vertices of S. So union V in S of the neighborhood of V. So as is, I'm doing a union between the neighborhood. So the Hull's matching theorem, so for any bipartite graph with part X and Y, so the graph has a complete matching from X to Y if and only if the number of elements in the neighborhood of S is greater or equal to the number of vertices in S, and this is for every subset S in X. So I need to find all the subset in X, and if this is verified, this inequality is verified, it means that I have a complete matching from X to Y. I can find a complete matching. So this is a revisited slide. So we see that it has a complete matching. So I need to consider all subsets. So not just, for example, here I have just two examples. I have picked Rana and Jamila. So I would need to find the neighborhood. So Rana is the neighborhood of Rana is just E. As for Jamila, is V1, E1, and E2. So the neighborhood is equal to 4 elements. However, S is equal to 2, so 4 is greater than 2. So I need to do that for all the subsets. So it means that Jamila alone, Kamal alone, May alone, Rana alone, Walid alone, and then I'm picking 2 of each these, then 3, then 4, then all 5. So obviously I can show that I can find a maximum matching because already I have done this. So it has a maximum matching. So whenever I have X is equal to Y, like in this case, so this theorem is sometimes referred to as Hull's marriage theorem because it can be interpreted in the following way. So let's suppose that X is a set of man and Y are the set of a woman, such that every subset of n man there are at least n suitable women. So it's possible to find the perfect matching of the man with woman and marry them all in pairs. So this is very known theorem, which calls Hull's theorem, marriage theorem. So a bipartite graph with two sets of X and Y, where the number of elements or the number of vertices in X is equal to the number of vertices in Y. So it has a perfect matching if and only if the number of elements in the neighborhood of S is greater or equal to the number of vertices in S, and this is for every subset in X. So it's the same, but it's called Hull's marriage theorem. So let's move to more concepts concerning bipartite graph, but we are considering here regular bipartite graph. So for example, if I'm considering a regular one, so regular, it means they have all the same degree. So for example, I have here one regular bipartite graph. I have here, for example, two. So for example, here I have two K22, for example. So a regular bipartite graph must be equitable. So in order, so it has x and y have the same number of vertices. So we have a theorem here that if a graph, bipartite graph is regular, so obviously it has a perfect matching. So in this case, this is not a regular bipartite graph. So the converse is of course false. So as it's shown in this bipartite graph, so it has a perfect matching. However, so I can match this like this. However, this is not a regular graph. So if it's regular, it means it has a perfect matching. So we move to the systems of distinct representative. So we will consider here an example in order to understand where we can use the SDR concept. So let's suppose I have a department, like a computer science department. In our university, we have 4 professors, A, B, C, and D. And let's suppose we need to form 4 committees, A, B, C, and D. So let's suppose also that we agree that a new umbrella, so as if there's one above all these, there's an umbrella committee with one representative from each of the committees A, B, C, and D. So I need to represent A, B, C, and D by one professor. So the catch is that no professor who serves on the umbrella committee should represent more than one of the individual committees. So as if one would represent each committee. So in the language of combinatorics, in statistics, so we seek a system of distinct representative for the committees A, B, C, and D. So we need to represent A, B, C, and D by one person. So this is the example. So we have professors, so are represented by A, B, C, and D, and the committees are represented by small capital letters, small letters A, B, C, and D. So in order to search for a system of distinct representative, so it is exactly the problem of finding a matching from Y to X, not from X to Y, but from Y to X, because each committee, it should be represented by one professor. So, and obviously not all professors would need to serve if there is a large number of professors. So here, obviously I have just 4 professors, but if I have, for example, 10 professors and I just need to form 4 committees, or to find a representative for the 4 committees, I just need 4 professors. So the graph has a perfect matching, as we have said, so this can be accomplished. So in order to find that, I need to find a matching from Y to X and not from X to Y. As for more general matching, so we have discussed a technique which is the augmenting path. So the augmenting path applies to all graphs, not just for the bipartite graph. So, and there are other techniques for finding maximum matching, mainly the network flow technique that is used for the case of bipartite graph. So we'll cover this in the last chapter. However, we illustrated the technique on non-bipartite graph. So we will cover here a last algorithm, which is the Edmonds Blossom algorithm. So augmenting paths can be found within a non-bipartite graph, which can be modified to create a larger matching. So we have here the different definitions: flower, stem, and base. I will directly explain them on an example. So we have a graph, and obviously we have a matching M. So as you can see, I have those vertices, so match, those are matched, and so on. So for example, U and this vertex, they are unmatched or unsaturated. So given a graph and a matching, a flower, so is the union of 2 alternating passes from an unmatched vertex to an unmatched vertex. So where one pass has odd lengths and the other one has even length. So this is, for example, a flower. So I have here a pass, and here it's another pass. So I will repeat: a flower is the union of 2 alternating paths from an unsaturated vertex U to another vertex V, where one path has an odd length and the other one has an even length. So if you want an augmenting, so this is alternating, so I can stop here. If I want an alternating path, I can have this and I can have also this, but we are considering just alternating, not augmenting. So I have to find 2 alternating paths. One is odd and the other is even. So this stem, as you can see, is the maximal common initial path out of U. So this is the common and the initial pass. So it's common for the two alternating paths. So it ends with a vertex. We call it B, and the vertex B is called the base. So B is the base. So the blossom, this is another definition, is the odd cycle that is obtained by removing the stem from the flower. So this is the cycle that is obtained from the flower. So I will repeat. I have to find a flower. So a flower, it means the union of two alternating paths. One is odd and the other is even, and we should start from an unmatched vertex. The stem is the maximal common initial path. It ends with a vertex B, which is called the base. So the base, it contains the blossom, so it's the odd cycle. So more properties about that. So we know that the stem must be of even length. So since the last edge must be from the matching M, obviously, so it's an even length. The blossom is an odd cycle, so we represent it as C2K plus 1. Why? Because we have just K edges which are matched from M. For example, here I have C1, so K is equal to 1, and I have C3, so K is equal to 1. So K would give me the number of matched edges. So again, also every vertex of the blossom, as you can see, it's matched to some other vertices, other vertex. So every vertex of the blossom must be matched by M, since traveling some direction along the cycle will end with an edge from M. Also, the only edge that comes off the blossom, so this one that comes off the blossom, that are also from M, must be from the stem. So it comes off the blossom and it should be matched. Thus, any non-stem edges coming off the blossom must be unmatched, obviously. So if it like this one, it should be unmatched. So the base one should be matched, and the one that comes out of the blossom must be unmatched. So what we'll do that, we'll examine alternating paths originating from an unmatched vertex, so the same as the old algorithm. So when all alternating paths from U are being explored, so and if there are two passes to a vertex are found to end in different types of edges, so namely match and unmatched, then a blossom obviously has been discovered. So what we will do that, then we'll see it in a while in the animation. We will contract the blossom, we will remove the blossom. What does it mean, the blossom? The cycle here, I will remove it and I will consider as just one vertex. So if I can, after removing the blossom, I can find an augmenting path in the contracted graph, then we can find an augmenting path in the original graph by choosing the correct direction of the blossom. So let's see an example. So I have this graph. I have found a blossom, so I will contract it. I will remove the cycle here and I will replace it with just one vertex. Let's call it B, usually with the base. And then I have this graph. So as you can see, I can find here in the graph an augmenting path, because I can start from U and end in this vertex, and as you can see, it's alternating. So as we have learned before, I just need to flip the matching. So I will flip here, so U and this one, it will be matched, and so on. And then I know that B, this one should be matched, so obviously, and this one should be unmatched. So I can work on this in order to have it like this. So as you can see, I have found an augmenting path and an augmenting path. So like in the augmenting path algorithm, we can swap edges along this path, creating a larger matching while still maintaining the property of matching. So this is also a good idea, and this is the Edmonds blossom algorithm. However, it's very difficult to implement, and you can implement it too, and it could be a question in your exam. So we need to use the Edmonds blossom algorithm to find a maximum matching on the graph below, where the initial matching is shown in bold. So we have a matching, we have a graph, and we need to see, so obviously it's not a bipartite, it's a general graph. So what we can do is that I need to find a blossom. So I need to find a cycle, or I need to find a stem in order to find an augmenting path. So can you find a flower? So a stem and a base and a blossom. So a blossom, it should be a cycle. So obviously you can investigate here because there's a cycle. So obviously, yes, I can find two alternating paths. One is odd and the other is even. So I can consider UA BC and UA BDC. So one is odd, one is even. So we know that the stem is equal to UAB. So B is the base and BCD is the blossom. So I have identified the blossom. So let we have it here. So again, I will remove the blossom. I will contract it. So just one vertex. So let's say I have contracted with a capital B. So can I find here an augmenting path? So can I find an augmenting path, yes or no? So obviously I can start from UAB. So obviously I need to reach an unmatched vertex. So if I go B, I, H, E, F, G, so okay, it's also possible. So I have a lot of augmenting passes. So for example, UAB, EFG, I have others also. So what I can do that I need to swap the edges and then reconstruct the original graph. And now, so I have this. So obviously this is the maximum matching because all the vertices are matched. So as the conclusion, so matching, so as you can see, I also found in weighted graph, not just general graph, but in weighted, so the edges have weights. So in weighted, for example, job assignment problem, we have a bipartite graph where the parts consist of the applicant and the job respectively. So the weight on a particular edge, for example, give a comparative measure of how qualified an applicant could be for a job. So for example, if a weight is greater than the other weight, so indicates that between applicants, for example, one is more qualified than the other. So we may think of weight as scores on some job-related exam. So what we usually want to do in such problem is to maximize the sum of the weights on the edges of the matching. So as a challenge for you, so this is a graph with weight. So can you do a maximum weight matching? So you will see that if you try to do it, that even for this small weighted graph, the problem is very challenging. So, and I don't know if there's an optimized algorithm in order to find the maximum weight matching. And this is it for this important and very nice chapter. So if you have any questions, do not hesitate to use the forum or to write to me. And again, thanks for watching.